Okay, this is graphing transformations of functions part 2. So in the part 1 video, we looked at how placing numbers in different places in the equation affects the graph in different ways. This video is going to focus on describing the transformations and actually graphing them if I have multiple things going on all at once. So how are we going to graph a transformation? Well, we're going to look at our equation and figure out what the special notation is in the equation, and we're going to use that to help us determine what the parent function is. Once we know the parent function, we're then going to graph the parent function on our coordinate axes so we have an actual visual for the points that we're going to be transforming. Then we're going to go back to our equation. We're going to look at the placement of all the numbers in the equation and use the information from the previous video to describe what each of those numbers is doing to the graph. So is it reflecting it over the x-axis, vertical stretch or compression, left, right, or up or down? Then last, we're going to move each of the points of the parent functions based off of the description in step 3. Order of operations here matters, and why I'm saying that is because if I have a reflection or a vertical stretch or compression, I have to do those before I do any translating or counting up, down, left, or right. Otherwise, the graph will be incorrect. So because the reflection and the vertical stretch and compressions are multiplications of the height of the point, that's a multiplication, whereas the translations, the left, right, up, and down, those are additions or subtractions. So multiplication wins out. So reflect and stretch first, then translate second. So let's actually do it for a few examples. So I'll walk you through the process. Step 1 says take a look at this and look for any special notation. So in this guy, the special notation is right here. So I know that my parent is y equals the square root of x. So I either find a picture of the square root of x or I make a quick table of the square root of x. So if I'm making a table for the square root of x, I want to pick values of x that are perfect squares. So I'm going to go 0, 1, and 4. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. So I'm going to plot those points. So my parent graph, let's see here, goes here, here, and here. And I know that it has this kind of slow rising curved shape. So this is y equals the square root of x. That's what we're going to be transforming. Second, or it's actually third, it says go back to the equation and look for the numbers that have been added into the equation and describe the transformation. So my transformation has two parts, and I know that because I see two numbers in my equation. This 2 right here, let's highlight that. This 2 is going to give me something, and this plus 3 is going to give me something else. So remember, numbers out in front of our graph give us vertical changes. The number is a 2, so this is a vertical stretch by 2. And then this plus 3 was this inside the square root, so that means this is a left or right change. And I remember things inside are always opposite of what I want them to be. So this plus means I'm going left, and I'm going quantity of 3. So I have two things I need to do to my graph. I need to vertically stretch each point by 2, which means multiply the y's by 2 first. And then left 3 says count each point left 3 after I do that. Ready? 0, 0. When I multiply 0, the y value of this by 2, it goes nowhere. Like we knew that was going to happen. That point never gets stretched or reflected. So now I'm just going to take it and count it left 3. 1, 2, 3. So this is my new 0, 0. So negative 3, 0 is my new 0, 0. 1, 1. Vertically stretch it by 2. So take this height of 1 and multiply it by 2. 1 times 2 is 2. So that puts me there. But that's not my final point. I want to now move that left 3. 1, 2, 3. There it is. Last point, 4, 2. The height is 2. Multiply that height by 2. 2 times 2 is 4. So it becomes 4, 4. So that puts me here. Now I want to count that left 3. 1, 2, 3. So the x's is where it would be after the stretch, and then the dots are where it will be after the stretch and the translation. So I take these and I curve them so it keeps that parent shape. So this is y equals 2 times the square root of x plus 3. Okay. Things that I just want to point out, because when we're writing equations, these are the things we look for. The starting point got moved. This is saying went left 3. So we knew that because that's how we got it. But if I was writing the equation, I would look for that. This says it does not go up or down at all. Next thing I want to look for here is when I go over to the right of that 0.1, how far up or down is it going? And this guy is going up 2. That's the same as the number in front of the equation, my a value, and that's exactly as it should be. Okay, so 2 checks that we can give to ourselves. And that's the end of that graph. Let's try another one. All right, this one, here we go. X plus 3 squared minus 2. This guy right here is telling me that my parent is y equals x squared. So I'm going to put the points on for x squared. So 0 squared is 0. X is 1. 1 squared is 1. X is 2. 2 squared is 4. Negative 1 is x. Negative 1 squared is 1. If negative 2 is x, negative 2 squared is positive 4. This has that U shape. This is symmetrical. So I want all that going on in my picture. Verify that all that's happening. And you'll see that I'm not going to make it cross through 3 because the 3 points me like way up here someplace. I'm just going to stop it just after passing through 2. So this is y equals x squared. So now I want to come back over here and I want to figure out what is happening to my equation. So I have this plus 3 inside my function. So this is a left or right change, opposite of what I want it to be. So this graph is going to go left 3. And then this guy at the end, outside of my function, is my up or down transformation. So this guy is going down 2. So this is my transformation description. Okay, so there's no stretch here, right? There's no number out in front. There's no negative in front, so there's no reflection. So that means all I have to do to all these points in my parent function is count them, left 3 and down 2. It doesn't matter which we do first. There's no, makes no difference here. So I'm just going to start with my 0, 0 point because that's our most important. It's our vertex. It's going to be how we determine our range. So I'm going to go left 3, 1, 2, 3, down 2, 1, 2, and there it is. I'm going to do that for a few more points. So left 3, down 2. Left 3, down 2. Left 3, down 2. And that one I know is going to get reflected, so the other one would be right there. So there the points transform. Now I just need to make it look like the parabola shape. So I'm going to do that roughly. And that roughly. It's not perfect. It's wiggly. That's fine. Yours will likely not be perfect either. I don't need it to be, as long as I can see the exact points and see you trying to get through those points. So this is the graph for x plus 3 squared minus 2. Left 3 minus 2. Here's my left 3 minus 2 right there. It's always visible in that 0, 0 point. And then if I look for the a value, when I go over 1, I'm only going up 1, exactly as it should be, because there is no number there, so that a number is a 1. I did just mention something about domain and range. For all quadratics, the domain is always all reals. The range for this graph is dependent on the y. If you need more review on domain and range, there is a video in the quadratics unit talking about that. So this guy here would represent the range of this graph. Here's the lowest y, and it's everything above it. So as a result, my range will be y is greater than or equal to the y value of my vertex, which is negative 2. One more graph, because we haven't done a reflection yet, so we need to make sure we get a reflection in there. All right, so again, my special notation is giving me my parent graph. So that's this right here. So this is saying that the parent is y equals the cube root of x. Make sure that 3 is little and in that check. All right, so this table, I know it goes through, so this is x, this is the cube root of x. Okay, so I know it goes through 0, 0. I know the cube root of 1 is 1. The cube root of negative 1 is negative 1. So my points go here, here, and here. And the next point is actually all the way out at 8, 2. So just know that this graph is going to be kind of skinny and long. Okay, so as you connect these, have it kind of be shallow because it's not going to get to the height of 2 for a little while. Okay, so I'm not going to exaggerate anymore or do any more than I need to because I'm not quite sure where it's going to happen. So this is y is the cube root of x. Next, we said we want to describe transformation. So my transformation description, negative sign. The negative gives me a reflection. And we say we have to state how. So this reflection over the x-axis. This plus 1 is underneath, so please be careful. If this ended, this would not be underneath. So since this is underneath the equation, this is attached to the x, so this is going to be left or right. Remember, left or right is always opposite of what it seems, so plus 1 means left 1. All right, left 1. Reflect over the x-axis. We said earlier that we always have, oh, I forgot one thing. This is a huge thing to miss. I have that 3 right there. That 3 out in front means that I have a vertical stretch by 3. So please note the minus sign got described on its own. The 3 gets described separately. I never say I stretch by a negative amount. So the negative is always the reflection, the 3 is the stretch. So these first two guys I have to deal with, or sorry, the first and the third one, I had to do these first. These are both multiplications of the y value. So I'm going to multiply the y's of each of these points. I'm going to multiply them by 3 for the stretch and by the negative 1 for the reflection. So I'm going to do those at the same time. I'm going to just multiply the y's by negative 3. So first I'm going to do that. Second, I'm going to count left 1. Let's do it. Here we go. Height of 0. 0 never gets changed when I multiply it. So this guy is just going to go left 1, right there. Height of 1. 1 multiplied by negative 3 becomes negative 3. So this point, 1, 2, 3, goes to here with my reflection and my stretch, and then it goes left 1. Bam. Height of negative 1 here, multiply that by negative 3, it becomes a height of positive 3, so that puts me right there with my reflection and my stretch. Left 1 there. This needs to keep this funny, weird, flattened out shape, so I'm going to have to fight for that, because this is going to have to go like this way to keep that weird flat shape, and this guy is going to come down and go this way. It's very important that you turn them out so it keeps that cubed root shape and doesn't end up looking cubic. Okay? Again, this this negative 1, 0 shows me my left 1. That's the transformation of 0, 0, the turning point of this graph. And then if I look right 1 from there, and I see how far up or down it goes, I see this right here is down 3. That should be my A value, and ta-da, it is. So this is perfect. So this is the graph of y equals negative 3 cubed root of x plus 1. And that's an example of them all put together in conjunction with each other and how to use them all at the same time.